We're going to continue looking at more examples that are not exactly what we need for them to be in order for us to apply Fundamental Theorem of Calculus Part 2. We're going to have to do some things. We're going to have to use or apply some properties of the definite integral in order to be able to get it into the form that we need. So this would be a good time maybe to review those properties of the definite integral. We need the lower limit to be a constant. It's not. We need the upper limit to be a variable or a function that is given in terms of variables, and it is. So we don't have problems with the upper limit, we have problems with the lower limit. And so the property that we're going to use first here is that we can break up our limits of integration at any interior point. Remember that? At any interior point. And so we're going to have to get a little creative here. What interior point between 2x and x squared would we like to break this integral up over? We want to start at 2x and go up to something, right? And then we want to add to that, starting at that something that we broke the integral up over and stopping at x squared. And here's where we have to get creative. Remember that our lower limit just needs to be a constant, any constant value at all. And remember, when we apply Fundamental Theorem Part 2, that constant doesn't show up anywhere because we're differentiating and it differentiates to 0. So let's break it up over any constant we want to. For instance, 0. It doesn't matter what we break it up over as long as it's a constant. There we've used that we can break up, we've used that property of the definite integral. And remember also that the lower limit has to be a constant and the upper limit has to be a variable expression. This is just like our last example. If we pop a negative out front and use that property, I guess I should write that here, put a negative out front, and swap the limits. That's all we have to do. And we're guaranteed that since that's a property of the definite integral, that we're going to be working with the same function. We haven't changed the value of anything. We've just changed, using good, well-defined properties of the definite integral, we've just changed the way it looks. All right, and now we're ready to actually take the derivative. So it's the derivative of the outside on this first one, and we'll put our negative up here. The derivative of the outside, not changing the inside. For this integral, the inside is 2x, times the derivative of what's inside. And we're going to add to that, again, the derivative of the outside, not changing the inside. Here the inside is x squared, times the derivative of what's inside. Now we could clean that up if we wanted to. I'm not going to take time to do that here. But this is the derivative of the function that was defined to be this function right here. All right, so remember that. You're going to have to use properties of the definite integral when it comes to applying Fundamental Theorem Part 2. So here's just kind of a mixed bag. We'll end here on these examples, kind of a mixed bag of examples here. Here we have the function defined to be this integral, and they want us to find the derivative. So big F prime, in essence here, because my upper limit is just x, in essence what I'm going to get is just a variable change. I don't even really, in this context, have to go through that chain rule verbalization, because I know the derivative of what's inside is just times 1. And I know when I don't change inside, I'm just swapping my t for an x. So anything that's like that, this one's the same way as well. F prime of x is just going to be little f of t with t replaced with x. Remember again, I am taking the derivative of a definite integral. There is no plus c. I sometimes see students just arbitrarily pop in a plus c here or there. and that's not necessary. So taking the derivative here, it's the derivative of the outside, not changing the inside, times the derivative of what's inside. So 18x. Let's move up here to this one. This is another chain rule one where we should verbalize it. It's the derivative of the outside, not changing the inside, times the derivative of what's inside. All right? And lastly, here's a theory question. And if it works for a specific function, it ought to work for theory function as well. So it is the derivative of the outside. There's our function. I'll put parentheses everywhere there's a t. Not changing the inside times the derivative of what's inside. So there's the power of that verbalization for the chain rule for us. It even gets us through a very high order derivative using fundamental theorem part 2 that's definitely given to us as a theory. So there are a couple more examples here. These are released AP examples. We're given a function that is defined as an integral, and we're asked to take the derivative of it. So just like we did on those last examples, it is the derivative of the outside, not changing the inside, times the derivative of what's inside. So we're looking for 2x times the sine of x to the 6th. So there's the answer right there. When we raise a power to a power, this 3 right here doesn't apply to sine, it only applies to t. So that's why I put it up there like that. All right, let's look at this last example. The graph of f prime consisting of 2 line segments and a semicircle is shown at the right. Given that f of 2 equals 5, find first f of 1, then f of 4, then f of 8. This is my attempt to show you that we're dealing with an accumulation function. And when we are integrating a derivative, now we're kind of doing it differently. We're integrating a derivative function that in essence what we're going to get is we're just going to get that original function back. So here is the derivative f prime of x. So there is a point on f that is negative 2, 5. So once I get right here, this is x of negative 2, the output of the original function is 5. So what would the output of the original function be at x equal 1? That's what part A is asking for here. Well, I know if I start with a value of 5, that I can accumulate area in the plane starting at my lower limit of negative 2 and stopping at my upper limit of 1. So this may not look like it's fundamental theorem part 2, but it is. It's in a graphical setting. So I'm just going to accumulate that area. Well, I can find that area by using the area of a triangle. The base of this triangle is 3 units. The height of this triangle is also 3 units. So that's going to be 1/2 the base times the height. So there is our output at 1. Part B says, what is our output at 4? Well, we can start with our output at 1, which is 5 plus 9 halves, and we can subtract from that because here's 4. We're going to get negative area here, aren't we? So we would add a negative or subtract the area of this triangle. It has a base of 3. The height is right there. So we're subtracting 1/2 the base times the height. And there is the accumulation starting at negative 2, because that's where they started us at, and stopping at 4. All right, so I think you basically have the idea. We'll do C here real quick and finish up this video. So the output of the function at 8 is accumulating the area. We've already accumulated up to 4, so we might as well start there. That's 5 plus 9 halves minus, that's 3. And then we're going to add this area, and we'll stop here at 8. Well, this is a circle. There's the center. It's the upper hemisphere of a circle. So the radius of that circle is 2. So the area is going to be half the area of a circle, so half of pi r squared. And there is the output of our function at x equal 8. So again, it may not be very clear that it's fundamental theorem of calculus part 2. Here we're doing it analytically. Here we're accumulating area in the plane, which is fundamental theorem part 2, right? The accumulation function going from our lower limit to our upper limit. Okay, so that finishes up fundamental theorem part 2. Come next time, we'll do some homework problems, and this will lead naturally into the next lesson, which is functions defined as integrals.